Hello viewers, Wagadaruna is taking you through the story for A-Level Applied Mathematics. And this video I'm going to go through the topic of circular motion. So this video is suitable for students in both Senior 5 and Senior 6 offering Principal Mathematics as part of their combination. Now before we proceed, let's first look at the course outline of this paper. So Math Part 2 is divided into 3 parts. There's a part of statistics and probability, and these are the topics. Numerical methods, these are the topics. And mechanics, which is further divided into 3 parts. What is ticked is available on this platform, and what is not yet ticked will be uploaded with time. So in this video, I'm going to go through the topic of circular motion. There are books which are vital at this level. So for Principal Mathematics, there are 4 books. There is Math Paper 1, Math Paper 2, Termly Past Papers with marking guides, and Topical Question Bank. Subsidiary Math is only 1 book. For Physics, there are also 4 books. Physics Paper 1, Physics Paper 2, Topical Question Bank, and its solutions. So for any of these copies, contact the author on this contact. So now we can start our topic of circular motion. So circular motion, just as the word is the motion of a body moving in a circular path with uniform speed about a fixed point. So uniform velocity implies that the magnitude of velocity is the same throughout the motion of the body, but its direction changes. So let's start with this word, speed of a body in circular motion. So the speed of a body in a circle can be specified by either its speed along the tangent at any instant, which we call linear speed, or by its angular speed, omega. I think you saw this in the topic of simple harmonic motion. So angular speed or velocity is the rate of change of the angle of a body moving in a circle. Therefore, omega is denoted by d theta dt, and the units are radians per second. So let's consider a body moving in a circle, moving in a circular path or along the circumference of a circle of radius r and center O as shown below. So we shall need the center and the circle. Then at the point A, remember we have linear speed. Linear speed is tangential. So it will be a tangent at the circle at that point with this. Then at another point, so let's suppose that in time t, delta t, the particle moves from point A to a nearby point B through a small angle delta theta. So let that be the point B, meaning that you make the speed will be that. Remember, it's told us the magnitude is the same, it is only the direction which is changing. That is why we are saying here V and V. If it was changing here, it would be U and here it would be V to mean initial and final velocity. But the magnitude is the same. And the angle it makes in time t is delta theta, and the circle is of radius r. So the length of the arc AB from here to here, the length of the arc is given by radius times the angle, which is delta theta. As this arc is covered in time t at speed v, its length is also, remember we know that distance is speed times time. So because the arc is covered in time t, delta t, using a speed of v, it implies that distance is speed times time, which will be v delta t. So therefore, we shall come and equate the two because they are all equal to the length of the arc. So this is the length of the arc, this is the length of the arc, so we can equate the two. When we make V the subject, we shall come up with R delta theta over delta t. So as delta t tends to 0, this tends to d theta dt. And you already know that d theta dt is omega. But before that, let's first replace this with d theta dt to give you this. Then remember that d theta dt is omega, implying that V is equal to R omega. I think I can see that the formula is similar to the one for simple harmonic motion somehow. But this, for simple harmonic motion, this was the formula for maximum velocity. But here it is, because velocity is constant, the magnitude is constant, so this will be the formula throughout. You don't have minimum or maximum. Then we shall go to, that was speed, then we shall go to centripetal acceleration of a body. So this is the rate of change in velocity of a body moving in a circular path. And it's always in the direction towards the center of the circular path. Remember, for simple harmonic motion, acceleration was directed towards a fixed point. So even here in simple harmonic motion, centripetal, know that word, centripetal acceleration will always be directed towards the center of the circular path. So let's consider a body moving in a circular path of radius r and center O as shown below. So let it be initially at that point A. Therefore, the velocity will be tangential, linear speed. Then at point B, the velocity will also be tangential, so the direction will change, but the magnitude is the same. So that will be the small angle it makes, meaning that by geometry, this angle is equal to that angle. Then when I resolve this velocity horizontal, I'll come up with this. And vertically, I'll come up with this. Now, suppose that the particle travels from point A to point B in time delta t, and that the angle AOB expressed in radians is delta theta, as we have seen here. That means that the acceleration of the particle in the direction, note this word, in the direction AO, when it is at this point, the center is here, so the acceleration should be in the direction AO. That's what centripetal acceleration means. It is always towards the center. So that acceleration is known as centripetal acceleration, and it is given by, so let's see, given by change in velocity along AO, which is the center, from A to B, taken and over time taken to travel from A to B. So remember, we are dealing with this direction, which is upward. We are dealing with the vertical along AO. So at this point, this velocity is entirely horizontal, so vertical component will be 0. At this point, there is a vertical component here. So the change in velocity will be this vertical component minus this 0. That will be the change in velocity. And that's what is given here over the time taken. So simplifying this, we'll come up with this, and from here I realize that this is a small angle, so this approximates to delta theta. I think that's what we meant here. That sine and angle tends to us that very angle. So this will become d theta dt, which is here. But we know that d theta dt is equal to angular velocity, and also v is equal to r omega. So I'll come and substitute First of all, I substitute for d theta dt to give me v omega. Then I remember that if I want to express acceleration in terms of v and r, it means that I have to remove the r, I have to remove the omega from using this. So omega will be v over r, which is here. You end up with v squared over r. That is one way of representing centripetal acceleration in terms of v, linear speed, and radius. What if I want to express in terms of angular speed? So in that case, it means that here, where there was v, I'll replace it with r omega, and I'll end up with r omega squared. It is similar in simple harmonic motion. I think you realize that the formula for maximum acceleration, it was also this. And also formula for maximum velocity was this. So for circular motion, because this will be the same, so it is constant, therefore it is always r omega squared, and velocity is always r omega. Now those are the two formulas used to obtain centripetal acceleration. Then next is centripetal force on a body. So this is the force that acts on a body moving in a circular path and always directed towards the center. So the direction of centripetal force is the same direction of centripetal acceleration. Both are always towards the center. So if a mass m, if m is the mass of the body and F is the centripetal force, then we can get F using ma from Newton's second law, and we already know that A is v squared over r, or A is omega squared r. So those are the two formulas that can be used to obtain centripetal force, either mv squared over r, or you can use m omega squared r. Any of the two is okay, depending on what is given in the question. With that, we shall go through this question. Question 1 says, a body of mass 250 grams moves with its angular speed of 4 rad per second in a circular path of radius 3.5 meters. Calculate Roman 1, the speed of the body in meters per second. They want now linear speed. Roman 2, the time taken by the body to make a complete revolution, that is period of motion. Roman 3, centripetal acceleration of the body. And Roman 4, the force that must act on the body towards the center of the circular path, that means centripetal force. So let's start with Roman 1. First of all, you know that mass should be in kilograms. Then angular velocity is that, radius is that. Therefore, for speed, linear speed is r omega. Substitute for r omega, you come up with linear speed. Roman 2 was period of motion, which is 2 pi over omega. Substitute for omega to come up with this as the period. Roman 3, centripetal acceleration, which is v squared over r. So v squared r to come up with that. And lastly, centripetal force. So we can use any of the three. Since we already have acceleration, we shall use ma. So ma to come up with this as the centripetal force. Okay, so that was centripetal force and centripetal acceleration. Now we shall go to what we call motion in a horizontal circle. When a circle is described at a constant speed, there is an acceleration of constant magnitude, which is this, like I've already told you, and it is always towards the center, and there is no acceleration which is tangential. So in a circle, the acceleration is always towards the center. Tangential, there is no, because you can't resolve that. When you resolve to this tangent, it implies that it will be zero component, because of this is 90. Now, since there is an acceleration towards the center, it implies that there must be a force of constant magnitude acting towards the center. And I think you remember that force is called centripetal force. So the necessary force towards the center can be provided by a rotating string with one end fixed at the center, or by friction with the surface as a body moves in a horizontal circle. So for you to maintain circular motion, there should be a force which is directed towards the center. If you are using a string, it means that the tension, the component of the string towards the center, provides the necessary centripetal force. If not, the body lies on a rough table, so the friction towards the center will cause the circular motion. So for circular motion to occur, there must be centripetal force. The condition for radial acceleration, so that this word radial means towards the center, can be achieved when the circle is in a horizontal plane because the weight of the body acts vertically and has no component in direction of motion of the particle, which is horizontal. So there are various cases for horizontal motion, but let's begin with, and we shall look at them one by one. So let's start with a particle tied on a string, but moving with a horizontal circle. So that means that a particle P is attached to one end of the string, and the other end is attached to a point O, fixed point O, on a smooth horizontal surface. We are saying smooth because this time around it is the tension in the string which will provide the centripetal force. If there is no string, it means that this table should be rough. So the friction provides the necessary centripetal force. If the particle moves in a circle, the necessary centripetal force is provided by the tension in the string. So let's first make an illustration. So we have a particle P, one end has a particle, another end is fixed. And this will be the angular velocity, so it is moving. I think in O level you covered three-dimensional geometry, and I believe that with that knowledge you should be able to appreciate that this is a rectangle and also that is a circle. It is in that form of like an oval because it is three-dimensional geometry. Otherwise it should be in that form if you look from up. So this particle moves along that path. Let's try to show the motion. I want you to look at this particle. It will move along that line in that form. So that is the circular motion. But what provides the necessary centripetal force is the tension in the string. So we shall come and put the tension in the string. Then the particle has weight vertically downwards, and there is also normal reaction. So resolving vertically, this will be equal to this. What about resolving radially? Radially means towards the center. Resolving towards the center, this tension will provide the necessary centripetal force. Now here, in circular motion, it is somehow a little funny. Do you know what? Let's see this step. We are saying that T is equal to mv squared over r. And here we are saying T is equal to mr omega squared. So we are not seeing this one anywhere on the diagram. So why are we using it? It's because we have to use Newton's second law. F is equal to ma. So F is the necessary centripetal force, which is that, and it's equal to ma, which is mv squared over r. So this will not be shown on the diagram. What they can show is the centripetal acceleration, but this will not be shown. But always remember that when you resolve the forces towards the center, they must be equal to the centripetal acceleration, because a force towards the center is the one which provides the necessary centripetal force for circular motion to occur. Hope that is also clear. Because in Newton's laws of motion, we didn't have such. But here we should remember that always a force towards the center provides the necessary centripetal acceleration. And with that knowledge, you can go through these questions. Question 1, actually there are a number of questions. Question 1 says, one end of a light inelastic string of length 1 meter is fixed to a point O on the smooth horizontal table. Okay. A particle P of mass 2 kilograms attached to the other end of the string is given a blow which sets it moving in a circle on the plane with a constant angular velocity of 5 rad per second. Okay. Part A, find Roman 1, the force exerted on P by the table, and Roman 2, the tension in the string. And part B, state any assumption made as P travels with constant speed. So you have already seen a sketch, but still we have to redraw it here. It is the same sketch we saw earlier in the introduction bit of it. So this will be the angular velocity, and this will be the particle, and the other end of the string is fixed at point O. There will be tension, there will be weight, there will be normal reaction, and the radius of the circle is 1 meter. So resolving vertically, we have R equal to mg. We already saw that. M is this, G is that. You come up with 19.6. That is Roman 1. They wanted the force exerted on P by the table. That is called the reaction. Then part B or Roman 2, they want the tension in the string. So there we know that this one is towards the center, so it provides the necessary centripetal force. We are using mr omega squared because in the question you are given angular velocity. If we are given linear velocity, we would have used mv squared over r. So substitute for m, for r, and for omega squared to give you this as the answer. Then part B, state any assumption made as P travels with constant speed. So as P travels with constant speed, it's assumed that there is no tangential force, i.e. there is no friction between the particle and the plane. That is the assumption. If there was friction, then there would be a loss, meaning that the speed will keep on reducing. That was question 1. Question 2, one end of a light inelastic. So I'm interested in this word, it is a keyword, because along the way we shall realize that sometimes the string can be elastic. But for now, in this example, the string is inelastic. Of length 2.4 meters, is fixed to a point O on a smooth horizontal table. A particle P of mass 1.5 kilograms attached to the other end of the string is given a blow which sets it moving in a circle on the plane with constant speed of 4 meters per second. Now this is linear speed. Find Roman 1, the force exerted on P by the table, and Roman 2, the tension in the string. So we shall still redraw the same diagram we drew earlier. A particle fixed to a point O and linear speed, then the circular path and the tension. The circular path is of radius 2.4, tension towards the center is T, weight is that, and normal reaction is that. So in Question 1, we used this because it was angular velocity, but now linear velocity we shall use a straight line. Then we shall resolve vertically to come up with r equal to mg. So r is, m is that, g is that, to come up with the value of r as that. And that's what they wanted in Roman 1. For Roman 2, we shall resolve radially, or use Newton's law, second law radially. This provides the necessary centripetal force. So m v squared r, you come up with the tension. Question 3. One end of a light inelastic, still the string is inelastic, of length L is fixed to a point O on a smooth horizontal table. A particle P of mass 8 kilograms attached to the other end of the string is given a blow which sets it moving in a circle on a plane with constant speed of 5 meters per second. If the tension in the string is 25 newtons, find Roman 1 the force exerted on P by the table, and Roman 2 the value of L. So still we shall draw the same diagram: particle P, fixed point O, linear speed, circular path, radius, tension, weight, and normal reaction. Then we can do the resolving vertically. R is 8g, g is 9.8, you come up with 78.4. Then resolving radially, T provides the necessary centripetal force. So this is equal to mv squared over r. And in this case, r is the L. This length of the string is the radius. So I'll come and substitute for T, for M, for V squared, and for R. And simplify to make L the subject. So that's what they wanted. Question 4. Question 4 says a body of mass m kilograms lies on a smooth horizontal surface and is connected to a point O on the surface by a light elastic. Now in the first 3 questions, the string was inelastic. But now this one, the string is elastic. Meaning that you have to remember the topic of Hooke's law, or the topic of elasticity, which is already on this platform. Of natural length 50 centimeters and modulus 70 newtons. When the body moves in a horizontal circular path about O with constant speed of this, the extension in the string is 20 centimeters. Find the mass of the body. So shall come and draw the same diagram you have been drawing. Only this time the string is elastic. So that is the linear speed, circular path. This is the new length, original length plus extension. Tension, weight, normal reaction. Okay, so they want you to find the value of m. So we know that L is 0.5 and modulus velocity is 70. This V is that, extension is that. So radius, this radius will be equal to this extended length. So come and add the two and get the radius. Then by Hooke's law, we can get the tension, which is modulus velocity, extension, and original length to give you this. This force is directed towards the center, so it provides the necessary centripetal force. Therefore, you can come and substitute for T, which you already got, V squared, and R, to remain with M as the only unknown. So M will be 1.6 kilograms, and that's what they wanted. Question 5. A body of mass 5 kilograms lies on a smooth horizontal surface and is connected to a point O on the surface by a light elastic string of natural length 2.5 meters and modulus of elasticity 40 newtons. If the string extends by this, so this will be the extension, find the speed of the body. So you still need to draw the same diagram I've been drawing. This is the speed they want. That will be the radius of the circle, tension in the string, weight, normal reaction. So that is mass, length, Young's modulus of elasticity, and extension. So the radius is the extended length, which is this. By Hooke's law, tension can be equal to using that formula. So T will be equal to 8 newtons. Then applying Newton's law radially, T provides the necessary centripetal force, which is mv squared over r. So come and substitute for T, substitute for m, substitute for r, and make V the subject. So I'll simplify and make V the subject. That's what they wanted. Question 6 says, a body of mass 1.5 kilograms lies on a smooth horizontal surface and is connected to a point O on the surface by a light elastic string of natural length 2 meters and modulus of elasticity lambda. When the particle moves in a horizontal circle about O with a constant speed of 6 meters per second, the extension of the string is 0.4 meters. Find the value of lambda, which is modulus of elasticity. So we shall make our sketch. That is the linear speed, this is the circular path, and then the radius is the extended length, tension, weight, normal reaction. Then we shall go through the same procedure as before. Radius is the extended length. Applying Newton's law radially, T provides the necessary centripetal force. So substitute for m v squared r to give you the tension. Then by Hooke's law, T is given by that. So substitute for T for X and for L, after which you should make lambda the subject, and that's what they wanted. So that was the case of a particle on a string. Now we shall go to another case where the particle is placed on a rotating disk. So if a particle P rests on the surface of a rotating horizontal disk, the only horizontal force acting on the particle is the friction force between the particle and the surface of the disk. So it is this frictional force which will provide the necessary centripetal force. So let's make an illustration. We have a rotating disk rotating with an angular velocity omega and center O. So if I put a particle on that disk, remember the disk is rotating. So meaning that the force is 1 will be the weight because the particle has mass. Then the normal reaction because the particle is resting on another particle. And this will now be our radius, the distance between the two. Then the force, centripetal force here will be provided by the friction between the body and the disk. So for any particular surface, there will be a maximum value, F max, which is mu r, and then the particle will be on the point of slipping or sliding. So the frictional force mu r acting on P towards the center of the circle is acting towards the center of the circle because P has to be given a central acceleration in order to travel in a circle. So for circular motion, there must be centripetal acceleration and centripetal force. And remember, there is no friction tangentially because A has no tendency to move in that direction. So resolving vertically, we shall come up with that. Then applying Newton's law radially, F provides the necessary centripetal force. So there are two formulas. So if there is no relative movement of the particle to the disk, what will happen? It means that friction is smaller than mu r, which is its maximum value. So come and substitute for this centripetal force and that, you will come up with a condition for mu. So mu should be greater than v squared over rg. And therefore the least possible value of mu, or coefficient of friction, is v squared over rg. With that, we can go through this question. It says, a particle P of mass 0.5 kilograms lies on a horizontal disk which is rotating about its center O at 3 rad per second. And A is 0.8 meters from O. If the particle does not move relative to the disk, find the least possible value of mu, which is the coefficient of friction between the particle and the disk. So it is similar to our derivation. So we have that angular velocity, particle, weight, normal reaction. The distance from the center to the particle is 0.8. Centripetal force is F. Therefore, resolving vertically, this is equal to this, which gives you 4.9 newtons. Then resolving radially, F provides the necessary centripetal force. Then substitute for m, r, and omega squared to give you this. So if there is no relative motion of the particle and the disk, it implies that friction is smaller than mu r, and that friction or centripetal force is 3.6 mu r, which you also got here. That implies that mu is greater than or equal to 36 over 49, and that's what they wanted. So now we shall go to question 2. Question 2 says, a particle P is moving on the inner surface of a smooth hemispherical bowl with center O and radius 1.225 meters. The particle is describing a horizontal circle with a center C with an angular speed of 4 rad per second. Find Roman 1, the magnitude of the force exerted on P by the surface of the bowl. And Roman 2, the depth of C below O. So we shall need to make a sketch. So we have a hemisphere with center O and a particle P with an angular velocity of 4 rad per second moving in a horizontal circle. So the weight of that particle is 2.5 g, and the normal reaction is r. Normal reaction, this is 90, so it is radial towards the center. Therefore, if you elongate it further, it has to touch the center. So the center of the horizontal circle made by this particle is C, meaning the horizontal circle is in that form. Acceleration or centripetal acceleration is always towards the center. So Roman 1 for the horizontal circle, radius is PC. From here, T as the radius. And it is got by resolving, because we know that this is 1.225 and this is the angle. So resolving horizontally, it gives you 1.225 sine theta. Then applying Newton's law horizontally. Now here we are saying horizontally, because now this will be the horizontal. But if you say radially, if you want to change this to radio, it means that this, you are taking this as the center. So radial means towards the center C. So towards the center C, when I resolve, this is entirely vertical. So it has no component along that towards C. Meaning the only force which will provide the necessary centripetal force will be the normal reaction. So this normal reaction, the component horizontally will provide the necessary centripetal force. That is why you see here r sine theta, which is the horizontal component of this, will be equal to the centripetal force. Then I'll substitute for m, r, remember r was this, and omega. So from there, I realize that this and this can cancel. So you can remain with, okay, I've just simplified there, but this will still cancel to remain with r as 49. Then they want the depth. So resolving vertically, you'll come up with r cos theta equal to 1 point, which is equal to the weight. So come and substitute for g to come up with the value of theta. So after getting theta, it means I can go back to this, or this from the diagram. You see this OC, it is the depth they want. So this OC means you resolve this length, which is here, you resolve it vertically. It will become 1.225 cos theta. Which will be equal to that. And that's what they wanted. Then that was motion in a horizontal circle. Then a conical pendulum is also motion in a horizontal circle, but somehow funny. Conical means it comes from the word cone. So let's see how this one is. So consider a body of mass m attached to the lower end of a light inextensible. Remember we said the string can, now that we have already covered the topic of elasticity, it implies the string can either be inelastic or elastic. So always find out. In this case, we shall consider a string which is inelastic, the upper end of which is fixed when the body is whirled in a horizontal circle of radius r at a constant speed v. The string describes a curved surface of the cone and turns at a constant angle theta, as shown below. This arrangement is known as a conical pendulum. So conical coming from the word cone. So let's try to see how this cone is. So I have a string attached at this point, but the angular velocity is in that form to form a horizontal circle. So the string is inclined at an angle theta to the vertical. So where is the word cone? If you take at this point, you realize that this will be the shape of a cone. So that is why they call it a conical pendulum. So there will be weight, there will be tension with arrows pointing each other. Now we have three lengths because this is a right angle. So this hypotenuse is what will be the length of the string. Okay, and it will be denoted by L. In this part of conical pendulum, that will be denoted by M. Then this one, vertical height, will be denoted by small h. And this one, horizontal length, will be denoted by the radius, coming from the radius of this horizontal circle. So when you say us write L, it means length of the string, or the hypotenuse. Then if you write R, it means this, and H, it means the vertical height. So that we can resolve also. Resolving vertically, we shall come up with T cos theta is equal to mg. Applying Newton's law horizontally or towards center O, we shall come up with T sine theta is equal to centripetal force, because that horizontal component is what provides the necessary centripetal force. Then dividing the two equations, you'll be able to eliminate T and remain with theta. Even here, this, I can get the reciprocal. So let's do that in the next slide. So sine theta over cos theta is tan theta, and this will come up with this. You realize that M can cancel. Then V can be made the subject. So that's the expression for the velocity of the particle. Now from triangle AOB, from this triangle, remember we have got these lengths. So I can get, from using SOHCAHTOA, I can get sine theta, cos theta, and tan theta. For example, sine theta is opposite over hypotenuse. So it will be R over L. Cos theta is adjacent over hypotenuse. So it will be H over L. Tan theta is opposite over adjacent, so it will be R over H. So let's go and write that. When I cross multiply, I'll come up with R equal to L sine theta, H is equal to L cos theta, and R is equal to H tan theta. So if I want to get R in terms of given H and theta, I can use this. R given L and theta, I use that. And H given L and theta, I can use that. So these ones are very vital because they will also be used to help us in the calculations. With that, we shall go through these questions. Question 1 came from UNEB of 1996, paper 2, question 11A, and says, a conical pendulum consists of a light inextensible string AB of length 50 centimeters, fixed at A and carrying a bob of mass 2 kilograms at B. The bob describes a horizontal circle about the vertical through A, with a constant angular speed of A rad per minute. Remember, the SI unit is rad per second, but this is now rad per minute. Find the tension in the string. So we shall come and make a sketch. There will be angular velocity, weight, tension in the string, inclination, radius. Then resolving vertically, t cos theta is equal to 2g. Then horizontally, t sin theta is equal to mr omega squared. So we shall come and substitute for r. Remember, r we said it is equal to L sin theta. Then omega, it will be A over 60. Why? Because it was per minute, but for us we're interested in per second. So 1 minute is equal to 60 seconds, implying that per minute will be 1 over 60 per second. Then m is that. So when you simplify, this will go with this, remain with t as that. And that's what they wanted. So now we shall go to question 2. Question 2 says, a conical pendulum consists of a light inextensible string, AB, of length 50 centimeters, fixed at A and carrying a bob of mass 2 kilograms at B. If the bob describes a horizontal circle about the vertical through A with a constant angular speed of 5 rads per second, calculate tension in the string, inclination of the string to the vertical, radius of the horizontal circle, velocity of the bob in meters per second, and lastly, the period of the bob. So one, we shall need to make a sketch which we have been making always for the conical pendulum. Particles there attached with an angular velocity and a horizontal circle. Then we shall put the inclination, the weight, the tension in the string. Then we shall start applying Newton's law horizontally. T sin theta is equal to the centripetal force. Then we can substitute, radius is that. I think remember that radius is L sin theta. So this sin theta can cancel. You remain with that. Therefore, I can now substitute to get the tension, mass, length, omega, to give you the tension of the string. That was Roman 1. Roman 2, they want the inclination. So inclination, we are going to resolve vertically to get t cos theta is equal to mg. Substitute for t, mg to get cos theta, then and lastly theta. So that will be the inclination to the vertical. Then Roman 3, they want the radius of the horizontal circle. We know that radius is L sin theta. So L sin theta to give you 0.3104. Then Roman 4, we shall go to they want the velocity of the bob in meters per second. So velocity is r square root of rg tan theta. So substitute for rg theta to give you this. Roman 5, I think it was period, period of the bob. We know that period is 2 pi over omega. So substitute for omega to come up with this as the period. So now we shall go to question 3. Question 3 says, a conical pendulum consists of a light elastic, this word elastic string AB of natural length 0.4 meters and modulus of elasticity 12 newtons, is fixed at A and carries a bob of mass 0.2 kilograms at B. If the bob describes a horizontal circle about the vertical through A, the extension in the string is 0.1 meters. Find Roman 1, the tension in the string, and Roman 2, the angular speed of the bob. So still we shall need to make a sketch of a conical pendulum. String is fixed at A and at B there is a particle attached. It moves the horizontal circle of angular velocity omega, which we don't know yet. Radius is r, we don't know it yet. Inclination to the vertical is theta. weight is 0.2 g, and this is the extended length, so it will be original length plus extension, which is that. So from Hooke's law, T is lambda, so modulus of elasticity, extension, original length. You'll come up with the tension as that. Then Roman 2, they want angular speed. So applying Newton's law horizontally, you'll come up with T sine theta equal to mr omega squared. And know that r is L sine theta. So this will cancel to remain with T equal to ml omega squared. Therefore, substitute for T, for M, for L, and remain with this as the unknown. Simplify to make omega the subject, and that's what they wanted. Then question 4 says a conical pendulum consists of a light elastic string AB of natural length L and modulus of elasticity 3 newtons, is fixed at A and carries a particle of mass 0.5 kilograms at B. If the particle describes a horizontal circle about the vertical through A with a constant angular speed of 5 rad per second, and that of the string is inclined at 60 degrees to the vertical, calculate Roman 1 the tension in the string, and Roman 2 the extended length, and Roman 3 the natural length. So still we shall need to draw a conical pendulum, same as we have been drawing before. That would be the angular velocity, which is unknown, horizontal circle, radius r, inclination is 60 to the vertical, weight 0.5 g, tension, and AB, which is the extended length. So Roman 1, they want tension in the string. So resolving vertically, we shall come up with T cos theta, T cos 60 degrees is equal to 0.5 g. Substitute for g and make T the subject. Roman 2, they want the extended length, they want AB. So applying Newton's law horizontally, we shall come up with T sine 60 is equal to mr omega squared. Then substitute this r the same as AB sine 60. So this sine and this sine cancels, remain with T equal to m times AB times omega squared. So we know this T, we know the omega, we know m, we can easily get AB, which is the extended length. And that's what they wanted in Roman 2. Then for Roman 3, they want the natural length. So we know that AB is equal to L plus X, implying that this is equal to L plus X, and extension is this. Therefore, by Hooke's law, T is equal to that, so come and substitute for X to remain with L as the only unknown. Cross multiply, collect like terms, and make L the subject. And that's what they wanted. Question 5. A light inextensible string of length this is attached to 2 points, A and B, where A is vertically above B and AB is 0.48 meters. Okay. If a smooth ring of mass 50 grams is threaded on the string and made to move in a horizontal circle about B, find Roman 1 the tension in the string, and Roman 2 the angular speed of the ring. So still to be a conical pendulum, but this time it is a little different because there is a certain mass which is being threaded, not attached. It is threaded on a string. So what is the difference? The difference is here. Here, initially it was only this string with a particle attached, but now this time the whole of this is the string and the particle is attached at a certain point along the string. And the word used is threaded, meaning the tension will be the same throughout because it is still continuous. The horizontal circle has angular velocity omega, which makes that horizontal circle. Then the weight is that, because this was grams, we have to change to kilograms for you to use that. Then the tension is still the same string, so it will be the same tension here, is the same tension here. So we know that AB is 0.48 and the whole of this length is this L plus R, which is 0.72. Meaning that L will be 0.72 minus R. And by Pythagoras theory, AB will be given by this hypotenuse minus this, which is L squared minus R squared, until they told us AB is 0.48. So square both sides and expand. Then here realize that we have one unknown. So make it the subject. And that will be the radius. Therefore L will be equal to this minus that to give you this. Resolving vertically, you come up with t cos theta equal to 0.05 g. Substitute for g, and this cos theta is the same as h over L. I think you remember that. Meaning that now that I know h and I know L and I know g, I can get the value of t. That was part A. Part B, the angular speed of the ring. So applying Newton's law horizontally. Now this is funny. Let's look at the diagram again. Remember we said centripetal force is provided by force towards the center. Now here there is this force, it is acting on the particle towards the center. Then there is also this other tension. When you resolve it, its horizontal component is towards the center. So there are two forces. One is the tension in this string BC and also the horizontal component of the tension in string SC. So that is the reason why we are seeing here T plus T sine theta equal to centripetal force. So sine theta is equal to R over L. Factorize out T, you come up with this. Then you can substitute for T, for R, for L, for M, for R. Then you remain with omega as the only unknown, which gives you that. So now we shall go to question 6. Question 6 says, a light inextensible string AB of length 33 centimeters has a particle of mass 50 grams attached. So if you don't realize the difference, in question 5, which is the previous question, they said threaded, but now here they are saying attached. To it at point P, 13 centimeters from end A. The ends of the string are attached to two fixed points in the same vertical line with A 21 centimeters above B. Okay, the particle moves in a horizontal circle 5 centimeters vertically below A with both parts of the string taut or tight at constant speed of this. Find the tensions in the two parts of the string. So here we shall need to make a sketch. There are 2 points, point A and point B. And those points are 21 meters apart. Then the particle, when it's making a horizontal circle, it is at this point. That will be the motion, and this horizontal circle will be that, with center O. This will be the radius, inclination of the first string, inclination of the second string. Now attached means these are two different strings, therefore the tensions will be different. First is the weight, which is that. Then the tension, arrows must face each other. Also tension here, arrows must face each other. They are different. Previously they were the same because it was threaded, but now this is just attached, so they are two different strings. Then this here, SC is 13, CB is 20, AB is 21, AO is 5, and the balance is 16. Then this is the radius. So for triangle AOC, Pythagoras theorem, we know that OC will be equal to this hypotenuse minus that. So come and substitute r squared is equal to 13 squared minus 5 squared to give you r squared equal to 144. Therefore r is 12 centimeters. Convert to meters, you come up with that. Therefore cos theta 1 is equal to AO over SC, which is this, and sin theta 1 is equal to OC over SC, which is that. Similarly, cos theta 2 is this, sin theta 2 is that. So with that, these will help us in resolving. So when I resolve vertically, I'll come up with that. Now the resolving is on the particle. Let's go back to the diagram. In resolving, we are interested on the forces acting on the particle, which are these ones. So vertically, there will be this angle is theta 1. So vertically, this one will be T1 cos theta 1, and downwards it will be this plus T2 cos theta 2. Which gives you that. Then we shall substitute for cos theta 1, cos theta 2, and for G to get an equation having both T1 and T2. Then also applying Newton's law horizontally, we shall have that. Then substitute for sin theta 1 and sin theta 2 to come up with an equation having both T1 and T2. So those are two equations, two unknowns. I can solve them simultaneously. And I'll come up with the value of T2. And then from equation 1, I can get the value of T1. And that's what they wanted. So now we have been dealing with motion in a horizontal circle, but now shall start motion in a vertical circle. So a particle can be made to travel in a vertical circular path in a variety of ways, but our study is limited to simple cases in which the speed of the particle, once it is set moving, is not affected by any external force other than weight. As the particle moves in a vertical circle, tangential component of weight varies, causing the speed of the particle to vary. That is, the speed of the particle decreases as the height of the particle increases. However, the total mechanical energy of the system remains constant. So there are various cases. Let's start with the first one of a particle attached on a string, and the particle makes a vertical circle. So consider a particle P of mass m suspended from a point O by an inextensible string of length r. Suppose the particle P is projected from its lowest position A with a horizontal speed u. The particle will move in a vertical circle of radius r as shown. So previously, we have been saying for horizontal circle, we have been saying that the magnitude of the speed is constant, does not change. But when it comes to the motion in the vertical circle, because acceleration due to gravity acts vertically downwards, the weight of the particle will cause the velocity to keep on reducing. So let's try to illustrate that. We have a circle with center O. Then a particle is attached at the lowest position A, and the speed is always tangential to the circular path. So this will be the initial velocity. After some time, the particle let it be at point B with a velocity v, and the height from the lowest position will be h. The forces now there will be weight on the particle, which acts vertically downwards. Then there will be tension in the string, which acts towards the center. And this angle here by geometry is equal to this, because these are corresponding angles. So with that, we can start by saying that conservation, because we said mechanical energy is conserved. So that means that mechanical energy at point A is equal to mechanical energy at point B. And I think remember that mechanical energy consists of kinetic and potential energy. So at point A, kinetic energy is this, but potential energy is 0 because this is the lowest point and it is used as the reference point. At point B, the velocity is this, therefore kinetic energy is this, and the height is that, which makes potential energy to be that. So this h, remember this is theta, the whole of this is r, but from here to here OC will be r cos theta. Therefore the remaining part, which is SC, will be r minus r cos theta. So simplify by removing the m first, then multiplying throughout by 2 to come up with a 2 there, which is this. Then factorize out r here to come up with this. That means that v can be given by this, and we shall call it equation 1. So applying Newton's law radially means along this line towards the center. So there is this force, but also this component, this weight has a component along that line, which will be mg cos theta. So the resultant force towards the center is one which provides the necessary centripetal force. And the resultant force towards the center will be T minus the mg cos theta. So you're coming and say that T minus mg cos theta is equal to the centripetal force. Multiply throughout by r to give you that. Then take this one this side to give you this. And that is equation 2. Now substituting for v, you will come up with this. Where there was v, we shall put there this. Then open this inner bracket to give you this. Collect like terms. This with this gives you this 3gr cos theta. And then you shall be able to come up with the expression for tension, which will be m over r, well, because this r came here, u squared minus 2gr plus 3gr cos theta. That is tension. Then for complete cycles, now if you look at this diagram, it is possible for this particle not to make a complete cycle. It may reach somewhere and then go back, or it may reach up and becomes slack, then falls down. So when does it form a complete cycle? For it to form a complete cycle, it means that at this highest position, tension must be greater than 0. So you shall come and say that tension is greater than 0 at the highest point, and at the highest point theta is 180 degrees. So come and substitute. Bring this tension here, but where there is theta, you put 180 degrees. Then you realize that cos 180 degrees is -1, so this becomes minus. Then you simplify this, and this gives you minus 5gr. Then this goes away, you remain with this, which will be greater than 0. Take this one this side to come up with this, and that will be the condition for complete cycle. The velocity, initial velocity at the lowest point must be greater than the square root of 5gr. So if u is exactly equal to square root of 5gr, it implies that the particle will just reach the highest point, after which the string will become slack. Slack means there will be no tension. It is just non-tight. So this likely question came from UNEB 1990 paper 2 question 9b. If you look at it, it is similar to the proof we have just made. The only difference is that where we used L as the length of the string, for them, where we used R as the length of the string, for them they used L as the length of the string. Otherwise, the others are all the same. So what you need to do is just go back to the proof you have made, and where there is R, you replace it with L. You'll be able to come up with the solution to this question. That was a particle in a string. Then part B is a particle inside a hollow spherical shell or a hemispherical bowl. So consider a particle projected horizontally with speed u from the lowest position A inside a smooth hollow sphere of radius r. The particle will move in a vertical circle of radius r as shown below. So we shall make a hollow hemispherical shell, and the particle is inside. So it is projected with a horizontal speed of u here at the lowest position. It will move, let's say, at point B. It has this velocity v, and the height from the lowest position is h. The weight of the particle will be mg, and the normal reaction will be r, but that reaction is towards the center. This angle is equal to this angle, corresponding angles by geometry. So applying Newton's law radially along this line OB, resultant will be r minus mg cos theta will provide the necessary centripetal force. Then rearrange, make r the subject, take this one this side to come up with this equation 1. Then by conservation of mechanical energy at point A is equal to that at point B. So come and get kinetic energy at A, potential energy at A, kinetic energy at B, potential energy at B. Then substitute for H. And then simplify, M will cancel, then multiply throughout by 2, come up with this and factorize out R. So making V squared the subject, you come up with that as equation 2. So this particle, which is moving inside the hollow spherical shell, may complete a cycle or it may not complete a cycle. So let's first look at a case where it does not complete a cycle. It means that it will move, and at a certain point it will lose contact with the inner surface. So in that case, it means that at the point where it loses contact, R is equal to 0. Therefore, we'll come and see that from equation 1, we got an expression of R. So where there is R, we shall put 0. Then you simplify, take on this side and cancel the m's. Then you get V squared as equation 3. Now we have V squared here and also V squared here. We can equate the two and come up with that. Then open brackets, collect like terms, meaning you can come up with the expression for U. This will be the expression for U, initial velocity. Then the other case is when the particle makes a complete cycle. For it to make a complete cycle, it implies that V must be greater than 0 at the highest point, or at the point when theta is 180. Meaning that here, from here, V is a square root. So put a square root and make it greater than 0. Square both sides and collect like terms, you realize that this gives you this, because cos 180 is -1. So 1 plus 1 is 2. 2 times this gives you 4. Then you'll make U the subject, and that will be the condition for complete cycle. It is a little different from the first one. So if U is equal to square root of 4gr, it implies the particle will just reach the highest point and then fall off. So now we shall go to question 1, which came from UNEB 2006, part 2, question 11b, and it says, a particle is placed on the lowest point of the inside of a smooth spherical shell of internal radius 3a meters and is given a horizontal velocity of root of 13 meters per second. How high above the point of projection does the particle rise? So we shall still make a sketch as we have made before. The lowest point with the velocity of u, then at point B it has a velocity of v, and the height h from the lowest point. Weight is mg, normal reaction towards the center is that. So we shall apply Newton's law radially at B to come up with this resultant force, providing the necessary centripetal force. Then at the point where the particle loses contact with the inner surface, R is equal to 0. So where there is R, you put 0. You'll come up with that as equation 1. Then by conservation of mechanical energy at A is equal to that at B. So this is equal to this, and we substitute kinetic energy at A, potential energy at A, kinetic energy at B, potential energy at B. So we shall come and substitute for U here and for H. Then simplify. First of all, m will cancel. Then 2 shall remember that r is equal to 3a. That is why you're seeing here 3a there. So substituting equation 1 into equation 2, it implies that you can substitute for this v squared here. Then you have to simplify. So what I've done here, I've multiplied throughout by 2 to give you this. Then I've opened brackets to get that. Then collecting like terms, this with this gives you negative 9 ag cos theta. Then this one going this side, it gives you 7 ag. So ag can cancel. You are going to remain with that, meaning that the angle of inclination is not acute, implying the particle passes through the highest point, and this means that it covers a vertical distance of 2r because diameter is 2r. r is 3a, so 2 times 3a gives you 6a meters before it loses contact. So now we shall go to question 2. Question 2 says a particle was projected with a speed of this from the lowest point inside a smooth sphere of radius r. Find the greatest height above the point of projection reached by the particle. So we shall first make a sketch of our hemisphere, of our spherical shell. This is the particle initially, and at a certain point, let it be at that point B with velocity v, and at a height h above the lowest point. Weight is that, normal reaction is that towards O, angle is that. So I'll apply Newton's law radially to give me that. So at the point where the particle loses contact with the inner surface of the sphere, r is equal to 0. So we shall come and substitute 0 here, and then we simplify to get equation 1. Then also by conservation of mechanical energy at A is equal to that at B. So we can substitute for this kinetic energy at A, potential energy at A, kinetic energy at B, potential energy at B. Then you substitute for initial velocity and also for h. Simplify to come up with that, collect like terms, you come up with that. Therefore v squared is equal to that. So those are two equations each for v squared, meaning you can equate the two. So when you equate, you shall come up with that and simplify to get cos theta, which is that. So now that we know cos theta, it means we can get h, because h is r minus r cos theta, which is r minus that to give you that. And that will be the greatest height reached. Then question 3 came from UNEB 2015, paper 2, question 8, and says a fixed hollow hemisphere of center O has center O and is fixed so that the plane of the rim is horizontal. A particle A of weight this can move on the inside surface of the hemisphere. The particle is acted upon by a horizontal force P, whose line of action is in a vertical plane through O. Okay, and OA makes an angle of 45 degrees to the vertical. If the coefficient of friction between the particle and the hemisphere is 0.5 and the particle is just about to slip downwards, find the normal reaction and the value of P. So first I need to make a sketch of our hemisphere, and then put a particle at a certain point where it is at the point of sliding downwards, but maintaining equilibrium with a force P, horizontal force P. Weight of that particle is this, and they told us that OA makes an angle of 45. That will be the normal reaction, and this is 45 with the vertical, giving you this as 45, and this also 45 by geometry. Then the friction is here, tangential. So resolving radially or parallel to OA, we shall come up with R being equal to this. Now here, it is different from the ones we have been doing because the ones I've been doing there has been motion, but now here it is in equilibrium, meaning that forces this side are equal to forces this side, and forces this side are there. We have this one. When I resolve it to this line radially, I'll come up with P cos 45. Then also this way, to resolve it along this line, I'll come up with 30 root 2 cos 45. Cos 45 is 1 over root 2, so I'll simplify this to come up with this. Therefore, friction is mu r. Our coefficient of friction is 0.5 times r to give you this. Then resolving tangentially over perpendicular at OA, we shall come up with this. Simplify to come up with this. Correct like terms. Then you'll be able to make P the subject, and that's what they wanted. They also wanted normal reaction. So normal reaction is that, so substitute for P, and you'll be able to get the normal reaction they wanted. So now we shall go to case of a particle on the outside surface of a solid sphere or hemisphere. So consider a particle of mass m released at rest from the highest point of a solid spherical object of radius r meters. The particle will move along the spherical surface up to a certain point where it will leave the surface. So let's try to illustrate that. So this time round, this hemisphere the sphere is solid, meaning the particle is outside on the outside surface of the sphere. So initially the velocity is 0. At a certain point B, it will have a velocity v, and the vertical distance will be h. This will be centripetal acceleration acting towards the center, and the weight will be this, and the normal reaction will be that. So applying Newton's law radially, we shall come up with resultant towards the center. There is this component here which will be mg cos theta, and this r which will oppose to be minus r to give you centripetal force. So if the particle leaves the sphere at point B, it implies that at that point r is equal to 0. So shall come and replace r with 0, then simplify to get equation 2. Then by conservation of mechanical energy at A is equal to that at B. Therefore, I'll come and substitute for potential energy, kinetic energy, potential energy, kinetic energy. Substitute for H and also for V. Then simplify and collect like terms. When I collect like terms, I'll come up with cos theta being equal to 2 over 3. Therefore, theta is 48.19 degrees. By geometry, theta will be equal to the angle to the horizontal at the point where the particle leaves the surface. And beta will be the angle to the vertical at the point where the particle leaves the surface. Therefore, beta will be 90 minus theta to give you this. the velocity v of at the point where the particle leaves the spherical surface can be got from equation 2 as follows. Because we already know that at that point cos theta is this, so I can come and substitute for cos theta, and I'll come up with this as the expression for velocity at that point. So note that the horizontal distance traveled by the particle while on the surface of the sphere will be equal to r sine theta. Let's go back to the diagram. So here, the horizontal distance will be from here up to here. Therefore, if this is r and this is theta, it implies that resolving to give you r sine theta. So this likely question came in 2013 paper 2 question 8. It is similar to the one you have just derived. So I won't repeat it. Let me go straight to question 2. Question 2 says a sphere whose radius is 4 meters is fixed on a horizontal plane. A particle of mass 5 kilograms is just displaced from rest at the highest point of a solid hemisphere of a solid spherical object of radius 4 meters. Find part A, the angle to the vertical at which the particle leaves the sphere. Part B, the horizontal distance from the point where the particle leaves the hemispherical surface to the point where it hits the horizontal plane. Part C, the speed with which the particle hits the horizontal plane. So we shall still make a sketch. So we have a particle initial at point A with velocity 0, then at point B with velocity v, moving a vertical distance of h. Then the centripetal acceleration, the weight, and the normal reaction. So applying Newton's law radially, this will give you that. This will provide the necessary centripetal force. Then at the point where the particle loses contact, we already know that r is equal to 0. So come and substitute, we'll come up with this. We already saw that. Then come and substitute for r and for g. You will come up with this as equation 1. Then by conservation of mechanical energy, we have this. So substitute for kinetic energy and potential energy. Let's do that in the next slide. To come up with that. Then substitute for h and for v squared. You will come up with this. Then r can cancel and g can cancel. You come up with this. So I think really it is the same procedure you have already derived. So part A was already derived, but we had to repeat it. So angle to the vertical will be better, which is that, as we already saw. Now our interest is part B. So at part B, at the point where it loses contact, let the vertical height from the ground be y. So and it has a velocity v with an angle theta to the horizontal. So it moves as a projectile up to point E with a horizontal distance x. So from equation 1, we know that v is equal to that. That was substitute because we already know that at this point cos theta is 2/3. meaning you will be able to get the value of V. Then Y from the diagram will be DO plus OC, which is R plus R cos theta. So R cos theta to come up with that. So now I know Y, I know V, I can now get, and I know tan theta is that. So using the equation of trajectory, I'll come up with this. Then we substitute for Y, for tan theta, for G, for V squared, and for cos theta squared. So when we simplify, we shall come up with this, which gives us a quadratic equation. It can be solved using bulldozer method to give you two values, and we shall ignore the negative value and take the positive value as the horizontal distance. Then for part C, they said find the speed with which the particle hits the horizontal plane. So by conservation of energy, we know that, therefore we shall come and substitute kinetic energy, potential, kinetic energy, potential. So now here, there is something funny. What do you know what I've done? 1, I have cancelled out the m's, and 2, I have multiplied throughout by 2. So this cancels here, there is 2, and here it cancels. So now here I have only V squared, which is this, because V was this, so when I square I come up with this. Here I have 2gy, and here I have V squared. So simplifying, I'll be able to get the value of velocity at the point of when it hits the ground. And that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on motion in a Cartesian plane. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. Also, if you know any student who's not yet on this platform, please share the link of this video with them by social media platforms like Facebook and WhatsApp so that can all benefit as a family.